Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Quantum Mechanics 1 with the course code PHY 212, we are at the lecture number 24 and the topic is degeneracy. In quantum mechanics, we can have a situation in which two states can have the same eigenvalues for any particle, or even more than two states can have the same eigenvalues. In such situation, we say that an operator is a degenerate operator and the state is degenerate, and this concept is called degeneracy. It's an important concept, and we find this in energy eigenvalues and momentum eigenvalues when there are different states corresponding to only one eigenvalue. So, in order to establish the concept, we start with doubly degenerate states. So, by doubly degenerate states, we mean that there are two distinct states which correspond to same eigenvalue. So, let us say we have an operator A and we have a state function phi 1. And this operator A can correspond to any physical observable. For example, it can be position, or it can be momentum, or it can be energy, or it can be angular momentum as well. And when this operator acts on this wave function phi, this is a state function, and since it's an eigen function, it will be reproduced. As you can see on the right side, when this A hat is acting on phi 1, then this phi 1 is coming again. This is the definition of eigen function, that the state function is reproduced after the action of an operator, but with multiplied with some constant which we call an eigenvalue, and this eigenvalue is a physically measurable value for the observable which is associated with this operator. So, when this operator acts corresponding to any observable, for example, if it's a position operator, or let us say a momentum operator, when it acts on the phi 1, it gives us one of the possible values a momentum can have for this particle and the states coming back. Now, let us say we have another state phi 2 which is distinct from phi 1, that is not equal to phi 1, it is totally a different state, but the same operator A is acting on this state and reproducing this state again phi 2. And this eigenvalue A. So, here you can note an important thing, that in both cases, when this operator was acting on phi 1 and when this operator was acting on phi 2, in both cases it has reproduced the same eigenvalue A. If this is the case, that for two distinct eigenstates, when operator is same operator is acting on them, is giving us the same eigenvalue, we say that this is degenerate, that the two different eigenstates or eigenfunctions are corresponding to same eigenvalue, we call them degenerate states. And in this example, since there are only two of them, and there are only two of them, not more, so we say that it is a doubly degenerate. These are the doubly degenerate states. So, eigenvalue is doubly degenerate. So, because this eigenvalue can come from phi 1 and can also come from phi 2 for this operator, we say that this eigenvalue is doubly degenerate. It can be possible that it is there is another state, that is phi 3, then we will say that it is a triple degenerate, or phi 4 and so on. So, we can have n-fold degeneracy, where n is the number of states we have for certain eigenvalue. So, this was the basic concept of degeneracy, in a simple one, that when you have number of states corresponding to same eigenvalue for some particular operator, then we say that these eigenvalues are degenerate. Okay, let us make it further in more detail. The first question arises from here is, if this A has eigenstate phi 1 and also has a phi 2, so what is the most general eigenstate then? What is the most general eigenstate which corresponds to A? And the answer is, if we can combine phi 1 and phi 2, if we combine phi 1 and phi 2, and with some arbitrary constants alpha and beta. And then this is the most general eigenstate an operator can have, and we call it, let's say, phi a, and here the subscript phi a denotes the eigenvalue for this operator when operator acting on phi and producing this eigenvalue. So we have subscripted this most general eigenstate with eigenvalue. So these are the arbitrary constants. Alpha beta are the arbitrary constants which we can determine, and let's test now if it is an eigen state of a operator A for an eigenvalue A. So what we have to do is we have to act on this phi A with an operator. So we have here in this line you can see this calculation. When we act with this operator A hat on the phi A, what we get, we have to plug in here the value of phi A, that is alpha phi 1 and beta phi 2, and now there are two terms. This is the first term on which this operator will act, alpha is constant, will go away, and then there is a second term on this which operator will act, and this beta is constant will go away. And the first term we get this after operator is acting, we will get alpha A phi 1, because we know when A hat acting on phi 1 give us A phi 1, and when this second thing will give us this one, and beta A phi 2, but A is common between them, so we can just take it out. So this will be A alpha phi 1 phi 2, and you have seen that now this is the eigen function, this phi A, which is I mean we can write it like here A phi A. So because this is equal to phi A, so this value here phi A, so which means that this phi A is also an eigen function corresponding to the same eigenvalue. Okay, so by this way we have seen we can construct the most general eigen function out of the degenerate eigen functions. Okay, so next is the geometrical interpretation. Why we have constructed this most general eigen function? In order to give you the idea that in Hilbert space, in this Hilbert space, where are the, which is spanned by only two unit vectors or two bases, that is phi 1 and phi 2. So this is a plane, and because this you can see these two relations that phi 1 and phi 2 are the eigen functions of A. So in this plane there can lie only eigen functions of this operator A. So you can see this is the most general situation where we combine phi 1 and phi 2 together to get another phi. So in Hilbert space sense, we say that these degenerate eigen functions are linearly independent, and they comprise they span the Hilbert space, and their any combination gives us another vector in this space. And if there is another combination, I mean depending on the value of alpha beta, we can you can change the orientation, but this vector will always lie in this Hilbert space, which is spanned by phi 1 and phi 2. Okay, now an interesting question arises that what are the eigenstates of degenerate operators, and here we will use this commutation relations we have developed in the previous lecture. That when we know that phi 1 is eigen function of A corresponding to the eigenvalue of A. So if I act with two operators, if I have two operators B and A, and I act with A first on phi 1, what I will get from here A phi 1, and A phi 1, and since A is constant, I can just take it out, and then B will act on it. So there is B phi 1. But since we also know, or you can write it like this, that because of the commuting property, because these are the two commuting operators, that B A could be equal to AB. Same will be the case over here if A is acting on B phi 1, because you see that if this is some state on which A acts with I mean this you can write it, if you calculate this thing, this must be because A is acting on it, and since this thing is equal to A, so A is the eigenvalue as over here, and this is the eigen function of the operator A. So we have just written over here that this B phi 1 is the eigen function of operator A. So just read it from here. So when A acting on B phi 1, what is giving it us? B phi 1 coming back with the eigenvalue A. So read from here the back side. When A acting on B phi 1, let's say call B phi 1 is equal to, let's say, phi 3. So A acting on phi 3 giving us this phi 3 back, because it is B phi 1 and with eigenvalue A. So that's why this relation exists. Okay. So B phi 1 is an eigenstate of A. So we have shown that B phi 1, which you can just say that it is, let's say, phi 3. Just to make it intuitive, clear to you, B phi 3 is B phi 1, which is the eigenstate of A. So we say that there is a continuum of eigenstates, because B phi 1, if I act with a B phi 1, could be written as mu alpha phi 1 B phi 2, because from the commutation property we know that this B phi 1 could be written as a linear combination. Phi 1 could be the linear combination alpha phi 1 and beta phi 2. So there could be some eigenvalue for operator B. So so the thing is that here you put the most general solution we have determined there, and when you put most general solution in phi 1, this is the most general solution, alpha phi 1 plus alpha phi 2. This is mu is acting here. So B phi 1 could be mu, where mu is some eigenvalue corresponding to the operator B. Okay. So in this case we see that phi 1 need not be the eigenvalue of B. Why? Because when B is acting on phi 1, it is not reproducing phi 1 alone, it is reproducing beta phi 2 as well. So it means that phi 1 is not the need not necessarily, if beta is 0, then it is possible. For beta is equal to 0, it is possible that this is the eigenvalue, but not necessarily it is the eigen function of B, because it is not reproducing it in the most general case when we replace phi 1 with alpha phi 1 plus beta phi 2, or when we replace this with the most general solution. So it means that when phi 1 was the eigenstate of operator A, it was not the eigenstate of operator B. And from here we conclude that the degenerate operators have more eigenvalues than non-degenerate operators. A was degenerate because it was there were at least two states corresponding to same eigenvalue, but B is not non-degenerate. So we see that A has more eigenvalues than B. So we are actually getting to a rule where we say that if A and B commute and A is a degenerate eigenvalue of an operator A, then the corresponding eigenfunction of A need not be the eigenfunction of B, as we have seen in the last case over here, that this was the eigenfunction of A, but it was not the necessarily eigenfunction of B. So what we are saying, that if there are two operators A and B, they are commuting, and A is the degenerate eigenvalue of A, then the corresponding eigenfunction of A need not be the eigenfunction of B. Although it was an eigenfunction of A, but it is not the eigenfunction of B, which means that B has less eigenfunctions than A, but A was degenerate, which means the degenerate operators have more eigenfunctions than non-degenerate operators. So this is an important rule. I repeat, if two operators commute and one of them is a degenerate operator having eigenvalue A and other is not, then this A will have more eigenvalues because it's degenerate. Since B is non-degenerate, it will have less eigenvalues. To make this concrete, let's go to the Venn diagrams and give you all the situations. For example, if we have eigenfunctions of A equal to eigenfunctions of B, in this case you can write this, you can generate this Venn diagram here. This circle is representing the eigenvalues, eigenfunctions of phi A is the eigenfunctions of operator A, and phi B is the eigenfunctions of, this is the eigenfunction of operator A, and this is the eigenfunction of operator B, and you see that they have the same eigenfunctions. So all the eigenfunctions of A is equal to all eigenfunctions of B. But what if one of them is degenerate? Let's go first to the case when A has only non-degenerate eigenfunctions. So if A has a non-degenerate eigenfunctions, so phi B is a degenerate, it has all values, but phi A has lesser values because these are the non-degenerate. And as I told you, the degenerate operators have more eigenvalues than non-degenerate. So this red circle here, red sphere here, showing the value of non-degenerate, because A is non-degenerate in this example, and B is degenerate. So degeneracy having more eigenvalues than non-degeneracy. Or you can just simply invert this one when B has only non-degenerate. So you can see that phi A is a bigger than phi B, because phi A is a degenerate eigenvalue and phi B is a non-degenerate eigenvalue, and they are less than them. Or we can make it more concrete when we say that, let's say there is another operator C, when AB is commuting, so this one is equal to 0, and B is commuting with a C equal to 0, and A is commuting with a C equal to 0. So they are all mutually commuting, A commuting with B, B commuting with C, and then A commuting with C. What will be the eigenvalues Venn diagram in this situation? In this situation, A has, let's imagine that A has only non-degenerate eigenfunctions. So I have phi C, which has complete eigenfunctions. I have phi B, which has this eigenfunction. They have their own eigenfunctions. And then there is an overlap between them, because some of the eigenfunctions just overlap. And then this is the degeneracy, because it's even less than the overlap. So this in overlap we have the eigenfunctions of C and B operators, but since A is degenerate, non-degenerate, so therefore this smaller set, this purple color, you can see the smaller set here. So what we wanted to establish, that the degenerate operators have more eigenvalues than the non-degenerate operators. In order to more clearly see again, we see an example. So consider we have a free particle moving in one dimension, like an electron. It is just, or any other particle, there are no forces acting on it, but it's just moving in one dimension freely. Its eigen energy is Ek h bar square by h bar square k square by 2m. Its eigenvalue for the energy. And then the corresponding operator is the Hamiltonian operator, because it's free. You can see no potential, so potential is 0. So h bar is equal to p square by 2m, and this is the corresponding eigenvalue for the energy, h bar square k square by 2m. Corresponding eigenfunctions are these could be the 3 eigenfunctions. I have given the example of 3 eigenfunctions, phi 1, phi 2, and phi 3. And here in the previous slides we have just seen the symbols, but now we have the functions as well. So phi 1 is cos kx, phi 2 is sin kx, and phi 3 is e raised to the power iota kx. So these are the 3 eigenfunctions corresponding to this h, giving this eigenvalue ek. So if you act on this h with h on this cos of x or sin of x or e raised to the power x, you will get this h bar square k square by 2m, because k's are here, it's integrable, and there are p square. You can see because of the p square, this is eigenvalue, because p square is p is I h bar del by del x. So del by del x, when it acts on one time, it will produce k, and cos will convert it to sine, and when it acts on the second time, it will produce another k. So you can see k square, h bar square coming from the definition of p, and 2m also coming from definition. So you see that this is the eigenfunction by just this calculation in head. And then you can also see this is also eigenfunction, because p acting 2 times will bring back the sign, and since it is a linear combination of both of them, it's obvious that it is also the eigenfunction. So we have seen that h is triply degenerate. This function, this function, this function, all giving the same eigenvalue. So this is this wave function giving this eigenvalue, this wave function giving eigenvalue, same eigenvalues. So 3 different wave functions give us only one eigenvalue. We say that this is degenerate. This eigenvalue is degenerate because it is coming from this function as well, this function as well, and this function as well. So now let's check that what are the linearly independent set of them. We want to see that if phi 1, phi 2, phi 3 are linearly independent or not. So if we check, we find out that these 2 are the linearly independent. Mind you that this third one is not linearly independent with them. Actually it is a linear combination of them. So phi 1 and phi 2 is cos kx. These are 2 linearly independent, and the eigenvalue corresponding to h bar k square by 2m, as we have seen. So if these are linearly independent, and we also know that the momentum operator commutes with the energy operator, ph is equal to 0. So we see that when there are n linearly independent eigenstates corresponding to same eigenvalue, the eigenvalue is n-fold degenerate. But on the other hand, you should also note in this slide that these wave functions or state functions are not eigen functions or operator p, because p by definition, as you know, minus I h bar del by del x, when this acts on it, it will convert cos into sine by this derivative. So it is not eigen function. You are not getting cos again. Similarly, if it acts on this, it will not. So these two are eigen functions of h, but these are not eigen functions of p. Actually, they are not. They are not necessarily eigen function of it. The third one was, because it was a linear combination, but this is not. So p has not these two eigen functions as eigen functions, but h has these eigen functions. But h is degenerate. So you can see that h is having more eigen functions than p. So if we even go back to this slide, you can see h has 3 eigen functions because it's a degenerate, but p has only 1 eigen function. So from this example, clearly you see that degenerate operators have more eigen functions than non-degenerate operators. So I hope this is now more clear. So another thing is the common so linearly independent set. So when there are n linearly independent eigenstates corresponding to same eigenvalue, the eigenvalue is n-fold degenerate. So we say that they are linearly independent, we say that this is n-fold degenerate. And then we can have common eigen states, we can construct out of them. For example, you can see we had phi 1 and phi 2, but when we linearly combined cos of kx plus iota sine of kx, we got e raised to power kx, and phi minus with the minus sign we have constructed, so e raised to power minus kx. So these are the two possible combinations, linear combination, e raised to power kx and e raised to power minus kx. But now these two are the common eigenstates of p and h because they commute. But these are these two combinations, not these not the individual ones. So this combination and this combination is the common eigenstates. So going back to here, you can see this was the common eigenstate for h and p both, but these two are not common eigenstates because they are not linearly independent. So when they are linearly independent set, we have eigenstates which are common to p and h because they commute. So common eigenstates of p and h we have just determined. So in this lecture we have seen the degeneracy. In physical system, we usually see that some of the states are degenerate, which means that corresponding to some operator, for example energy or momentum, if we apply them, they give us the same eigenvalue. So although there are 2 or 3 or more different eigenstates, but they give us just same eigenvalue for some operator. So these are called degenerate eigenstates, and then physically we have this concept of degeneracy in quantum mechanics. And then we have also discussed some of the simple properties of degenerate operators. With this, I thank you all.